Good morning and hi to everyone that watch our video. So today me and my group will present about our mini project steel design structure. So as you can see, the given at the picture is concrete steel roofing is 0.20 kN over meter square. Lightning and insulation 0.10 kN over meter square. Self-weight of purlin is 0.06 kN over meter square. Self-weight of trusses is 0.10 kN over meter square. And then the variable load on the slope QK is 0.60 kN over meter square. So that is the total of QK. So first one is we must total all the GK. So as you can see, the concrete steel roofing until self-weight of trusses, we must plus all, then we will get the total of GK. So after we plus all that number, we will get 0.46 kN over meter square. And step number 2 is steel design or steel load, which is we must calculate the GK and QK. So the formula is 1.35 multiplies GK plus 1.5 multiply QK. So 1.35 multiply 0.46 plus 1.5 multiply 0.60. So we will get the Q as total 1.52 kN over meter square. So next step is area A. So as you can see, there's given for SP and ST, which is SP is 2 and ST is 5. So 2 multiply 5, we will get 10 meters square. Then point load P equal Q multiply A, which is the Q is design load and then the A is area. So the total that we get for Q is 1.52 multiply 10 meters square. So we will get 15.2 kN. So that is the total truss analysis for each trusses load. So the next step is we must calculate the moment area, which is everything on the right must go to the left, which is RA multiply 16 minus 15.2 multiply 16 meter minus 15.2 multiply 12 meter minus 15.2 multiply 8 and minus 15.2 multiply 4 equals 0. So as you can see, RA multiply 16 minus 608 equals 0. As you can see, RA multiply 16 minus 608 equals 0. So everything that on the left, we will take and put it on the right. So RA equal 608 divided by 16, so we will get 38 kN. Next, for the Fx is equal 0 and Fy equals 0. REY plus 38 minus 15.2 minus 15.2 minus 15.2 minus 15.2 and minus 15.2 equals 0. So we will get REY equal 38 kN. To calculate from joint A. So from the given trusses, we observe a force of 7.6 Newton acting vertically downward. We resolve the forces using equilibrium equation. First, using the equation of vertical equilibrium is Fy equals 0. We calculate the vertical component of FAB, which is Fy equals 0 and then 3 divided by 5 FAB plus 3, 0.4 minus 3 divided by 5 FAB plus 30.4 minus 7.6 equals 0. So FAB will get negative 38 kilonewton. So we will change the negative and we will get the positive. So the new total is FAB equal 38 kilonewton. For the Fx, we will get FH plus 4 divided 5 multiply negative 38 equals 0. So we will get the new total for FH is 30.4 kilonewton. So next is for joint H. So as you can see, there is a horizontal line as F FAH equal 30.4 kN. So Fx is FHG minus 30.4 equals 0. So we will get FHG as positive 30.4 kN. Next, for Fy is 0, which is FBH equals 0 equal FFD. So there's no total for FHY. Joint B is, as you can see, there's a downward vertical which is 15.2 kN, and then we will calculate for two equations, for which is the first one is Fx equals 0. 4 divided 5 FBC plus 4 divided by 5 FBG minus 4 over 5 multiply negative 38 equals 0. So we will get the first equation is 0.8 FBC plus 0.8 FBG minus 20.4 equals 0. So next is Fy, which is 3 over 5 FBC minus 3 over 5 FBG minus 15.2 minus 2 over 5 equal negative 38 equals 0. So we will get the second equation is 0.6 FBC negative 0.6 FBG plus 7.6 equals 0. Then we will get the total for FBC is negative 25.33 equal 25.33C, and FBG is negative 12.67 equal 12.67. So at the next joint is joint C. There is a 15.4 kN force acting vertically downward, and FBC, which is we calculate as horizontal, negative 25.33 kN. So first, Fx equals 0, that give us negative 4 over 5 multiply negative 25.33 plus 4 over 5 FCD equal negative 21.57 kN. And for the Fy equals 0, we will have negative FCG minus 15.2 minus 2 over 5 multiply negative 25.33 minus 3 over 5 multiply negative 21.57 equals 0. At the left, we will have negative FCG equal negative 12.90. So we cut the negative and we will get 12.90 kNT. So for the highest compression tension is FAB equal 38 kN equal FAD, and then for the highest tension force is FAH 30.4 kN equal FHG. So for the next step is design of tension member. So I will show you guys, which is there is specific end member connected with 2 bolts, and then the highest tension force NED is 30.4 kN. The chosen an equal angle is 100 multiplied 75 multiplied 12 length. So as you can see, AS equal 1970 millimeter square, IY equal 31.0 millimeter, IZ equal 21.4 millimeter, IU equal 34.2 millimeter, IV equal 15.9 millimeter, and the last one is T equal 12 millimeter. So next is design strength, Fy, which is we will get at table 3.1. So which is T that I've told you guys already is 12 millimeter, must be smaller than 30 millimeter. So the steel grade that we choose is S275, and Fy equal 275 Newton over millimeter square, and Fu equal 430 Newton over millimeter square. Clause 6.2.3, diameter bolt D equal 20 millimeter, design tension resistant NERD should taken as the smallest of NP1 RD equal AFY over MO or NU over RD equals 0.9, and net FU over M2. So the design plastic resistance of the cross section NP1RD equal 1970 multiply 275 equal 10 negative 5 over 1, so we will get 541.75 kN. Then the next step is design ultimate resistance of the nut cross section at holes for fastener and URD equal 0.9 multiply 1655.8 multiply 430 multiply 10 minus 3 over 1.25, we will get NTRD 512.64 kN. Then from the clause 6.2.3 checking formula 6.5 NED over NTRD must smaller than 1.0. So 30.4 over 512.64, we will get 0.06 smaller than 1.0. Then the section for 100 multiply 75 multiply 12 length is suitable to carry the tension force. So 0.06 smaller than 1.0 is okay. For the last one is axial compression NED equal 38 kN. So sizing is still the same as the tension compression, which is 100 multiply 75 multiply 12 length. That all I get is from table property. So AS is still 1970 millimeter square, IY equal 12.0 millimeter, IZ equal 21.4 millimeter, IU equal 34.2 millimeter, IV equal 15.9 millimeter, and T equal 12 millimeter. So table 3.1 design strength Fy, which is T is 12 millimeter must smaller than 50 millimeter. So steel grade is the same S275, Fy equal 275 Newton over millimeter square, Fu equal 420 Newton over millimeter square. From table 5.2 is cross section H over T. So H is 100 over 12 millimeter equal 8.3 smaller than 15 T. So which is T is 0.92. So 15 multiply 0.92, we will get 13.8. And then the next formula is B plus H over 2T. So B is 75 and then H is 100, so 75 plus 100 over 2 multiply 12. T is 12 millimeter, and then we will get 7.29 smaller than 11.5. So E is 0.92 is still, so 11.5 multiply 0.92, so we'll get 10.58. Then for the IV is 15.9 millimeter, will contribute to the layout slenderness equal LCR over IV. So from the clause 6.3.1, hence V minus V is the weakness cause, and formula that we use is 6.49, which is NVRD equal XVFY over M1. In the clause 6.2.1.2, where the capacity of reduction factor is given, XV equal 1 over phi V plus square root phi V square minus XV is not more than 1.0. And then from clause 6.3.1.2, where PV equals 0.5, 1 plus lambda minus 0.2 bracket plus lambda square, and then lambda V equals equal square root AFY over NCR equal LCR over IV 1 over lambda 1. LCR 1.0, L equal 1.0 multiply 20 equal 20 millimeter. So x1 equal square root E over Fy equal 93.9 equal 93.9 multiply 0.92 equal 86.39. So we will get xv equal 20 over 15.9 multiply 1 over 6 multiply 1 over 86.39 equals 0.01. So from table 6.2 buckling curve A, table 6.1 factor equals 0.1, clause 6.3.1.2, which is V equals 0.5 bracket 1 plus 0.21 bracket 0.01 minus 0.2 bracket plus 0.01 square bracket equals 0.48. So lambda equal 1 over 0.48 plus square root 0.48 square minus 0.01, we will get 1.05. So from clause 6.3.1 and VBRD equal 1.05 multiply 1970 multiply 275 multiply 0 negative 3 over 1.0. So we will get the answer is 563.06 kN. So for the checking is NED over NVRD is not bigger than 1.0. So 38 over 563.06 equals 0.06 is lower than 1.0. Section 100 multiply 75 multiply 12 length is suitable. That is from me, JAWAHIR QURRATUAINI binti SAPARUDDIN. Thank you.
Hi everyone, my name is HANISAH NAZIRAH binti HAIRUDIN, matrix number 07DKA23F1041. Continuing from my friend's explanation on a roof truss mini project, and I will present the next part of our mini project, which is the beam analysis. So from the roof truss, we obtained that the GK is 0.46 kilonewton per meter square and the QK is 0.6 kilonewton per meter square. Now let's look at the beam details. So the beam is simply supported and it's divided into 4 equal spans. Each of the span is 4 meters and making the total span of 16 meters. Since the load is symmetrical, both ends carries the same value, which is 30.4 kilonewtons. Now we move on to draw SFD and BMD. First is SFD. It starts at positive 22.8 kilonewtons and decrease step by step as we move across the beam, and the ending we got is negative 22.8 kilonewtons. Next is the BMD. The highest moment is at the center of the beam, which is 121.6 kilonewton meters. But this is a typical shape of a simply support beam under uniform loading. So if you guys are wondering how I get those values, it's like this. We also learned this before, I think during semester 2 in subject Mechanics of Civil Engineering Structure, or most commonly known as MUTHIIAH. So from the table properties for beam, I choose the 762 times 267 times 197 UB, and I listed all the data needed from the table properties. So for classify cross-section, I refer from table 3.1 in Eurocode 3. TF is 25.4 mm and TW is 15.6 mm, meaning that the T is less than or equal to 40 mm. The steel grade is S275. Therefore, the Fy is 275 Newton per mm square and Fu is 430 Newton per mm square. So for E and G value, it's a fixed value. So you guys can refer in clause 3.2.6. So for clause 5.5.2, square root 235 divided by 275 equals to 0.92. So now we want to confirm which clause are for flange and web. After calculate using the formula for flange and web, and I know that both flange and web is class number 1. Next we check the bending resistance of beam and can refer class 6.2.5. Code formula we use is 6.55, which is for class number 1 and 2 sections. After calculate the value, I got 1971.8 kilonewton meters, which is much greater than the required bending moment of 121.6 kilonewton meters, meaning that the cross section is safe in bending. Next is a lateral torsional buckling check. Refer from class 6.3.2.2. We use the effective length of 4000 mm after convert and can calculate the buckling moment using the formula 6.55. But before that, we need to find the value of psi and C1 as shown to get the MCR value. To calculate psi and C1 and just insert the value in the MCR formula. After calculate, I got the MCR value is equal to 4353.76 times 10 to the power of 6 Newton millimeters. And after I convert to kilonewton meters, then I got 4354 kilonewton meters. Next, we calculate the non-dimensional slenderness. Formula is lambda bar equals square root 7170 times 10 to the power of 3 times 275 divided by 4354 times 10 to the power of 6, and the answer we got is 0.67. For selecting the buckling curve and imperfections factor, refer from table 6.4. H over P equals to 2.87, which is greater than 2. That means that a roller I section we use buckling curve is B. And the value we can refer from table 6.3 for buckling B is 0.34. Now from using the formula 6.56, which is to calculate the reduction factor for lateral torsional buckling. But the answer must be less than or equal to 1.0. So first we need to find value of phi so that we can use in finding the reduction factor. Phi is equals to 0.5 times open bracket 1 plus 0.34 open bracket 0.67 minus 0.2 close bracket plus 0.67 square close bracket, and the answer is 0.80. And now we calculate the chi LT equals to 1 divided by 0.8 plus square root of 0.8 square minus 0.67 square The answer for KLT is 0.90. From the formula 6.56, for MBRD we got 177.458 times 10 to the power of 6 Newton mm, and after convert I got 1775 kilonewtons meters. Now let's do the checking. The MED divided by MBRD, and we got the answer is 0.07, which less than 1. That means the beam BC for 762 times 267 times 197 as 275 is suitable. Now for AB. Do the same steps and use the same formula as the segment BC, but this one is start from C1. And the answer I got for C1 is 1.88, which is less than 2.70. Next is the MCR. Insert all the value using the same formula, and the answer is 8185 kilonewtons meters. For non-dimensional slenderness, I got is 0.49. Next is class 6.3.2.2. The reduction factor using 6.56 formula, and the answer is 0.89. From the formula 6.55, answer for MBRT is 1755 kilonewton meters. And lastly is the checking. As you guys can see, the answer is same as the segment BC, which is 0.07 less than 1, meaning that the bending is okay and the segment for AB is suitable. And that's all for my part.
Assalamualaikum and hi, my name is SYAHIRAH binti BAHRIN and my registration number is 07DKA23F1038. In this presentation, I would like to present about design of column. So refer to the table properties error code 3. For UC section, I choose 203 times 203 times 127. Based on beam analysis, our MED is 121.6 kilonewton and our MA is 30.4 kilonewton. Refer to the table 3.1. Our design steel is S275. Our T is less than 40 millimeter. So our Fy is 275 Newton per millimeter square. And our Fu is 430 Newton per millimeter square. Based on table 5.2, square root 235 over Fy, which is 275, equal to 0.92. Refer to the clause 5.5.2. Our classification flange is class 1 and our web also class 1. Therefore, overall section is class 1. Based on clause 6.2.4, compression, the formula I use is NCRD equal to AFY over gamma MO. And I got an answer 4,455 kilonewton. For buckling resistance, from clause 6.3.1.1, the formula is NB/RD equal X AFY over gamma M1, where X equal to 1 over 5 plus square root phi square minus lambda square, where phi equals 0.5 bracket 1 plus alpha bracket lambda minus 0.2 bracket plus lambda square. bracket. For lambda's formula is square root A Fy over NCR equal to LCR over I 1 over lambda 1. For class 1, 2, 3, lambda 1 equal to pi square root E over Fy. Based on table 6.1 and 6.2, H over B, I got 1.13, which is less than 1.2. TF equal to 30.1 mm, less than 100 mm. For buckling about YY, curve B, buckling about ZZ, curve C. So, buckling about major axis YY, lambda 1 is equal to 86.39. For buckling length is 6,000 mm. For lambda equal LCR over I 1 over lambda 1, I got 0.66. Based on table 6.1, buckling about YY curve B, hence alpha is 0.34, our phi is 0. Our x also equal to 0.80, which is less than 1.0. So our NBRD equal to 3,564 kilonewton. For buckling about major axis ZZ, our lambda 1 is equal 86.39. For buckling length is 6,000 mm and lambda equal LCR over I 1 over lambda 1 is 1.26. Also use table 6.1, which is buckling about ZZ curve C. Hence, alpha is equal 0.49. Our phi is 1.55. Our x is 0.41, which is less than 1.0. So our NBRD equal to 1,826.55 kilonewton. Based on MED and MA from the beam calculation, our column weight is 10.13 kilonewton. NED equal to 162.13 kilonewton, which is our NED is less than our column weight. Therefore, buckling resistance is okay. So, for the UC section 203 times 203 times 127 in grade S275 still is adequate. For interaction equation for column, which is NED over Nmin B RD plus MYED over MYRD plus 1.5 MZED over MZRD is less than 1.0. For NED, 162.13 kilonewton and min RD equal to 1,826.55 kilonewton, MYED equal to 6709.28, MYRD equal to 418000, MZED equal to 13260.48, and MZRD equal to 1936000. After the calculation, I got 0.21, which is less than 1.0. Therefore, UC section 203 times 203 times 127, steel grade S275 is suitable for this column. That's all from me. Thank you.
Hi everyone, my name is MUTHIIAH SUMMAYYAH. I will be presenting a design check of a bolt connection subjected to bolt, shear and torsional forces. The goal is to verify whether a 24mm diameter bolt of grade 5.6 is sufficient for the applied external loads. Let's begin with the design layout. The connection used a steel plate with a thickness of 20mm. There are 8 bolts arranged symmetrically in 4 rows. The applied external forces are 1 to 1.6 kN vertically and 30.4 kN horizontally. For this analysis, we use a 24mm diameter bolt with a 26mm hole. The bolt spacing is 100mm vertically and 50mm edge distance. First, we calculate the direct shear in bolt A. Since the force is shared equally among 8 bolts, so 1 to 1.6 kN divide 8 and equals 5.2 kN. Next, we calculate the shear due to torsion. We determine the polar moment of area using the coordinates of the bolt. This gives then Ft is equal to 48.06 kN. Now, we find the resultant shear force in bolt A. We use the vector formula Fr equals to square root Fs square plus Ft square plus 2 Fsft cos, with cos equals to 0.316, so Fr is equal to 54.79 kN. So the design shear force acting on the bolt is 54.79 kN. Now we check if the bolt can resist the shear. Using the code, bolt diameter equals to 24mm, threaded shear area is equal to 353mm square millimeter. Then FUB equals to 500 and YM2 equals to 1.25. Then FVRD is equals to 84.72 kN. So the bolt shear resistance is adequate. Next, we check the bearing resistance. From the formulas we calculate AB is equal to 1.16, K1 equals to 2.5, FBRD is equals to 264.2 kN. Since both shear and bearing resistance are greater than applied load, a 24mm diameter bolt of grade 5.6 is satisfactory for the connection. Next, we are given a load of 30.4 kN acting on a plate with bolts arranged in 4 rows. Each row is spaced 90mm apart, and the eccentricity of the load from the bolt group center is 250mm. We start by calculating the direct shear force per bolt using P equals to 30.4 kN and 10 bolts. So FVED is equals to 3.04 kN. Next, we calculate the tensile force due to eccentricity using this formula. We sum the square of distance from the centroid with Ymax equals to 360mm. So FTED is equals to 2.3 to times 10 to the power negative 5. According to table 3.1, for bolt grade 5.6 and A equals to 0.6, assuming shear occurs at the threaded section, A equals to 561 millimeter square. The shear resistance is FERD equals to 134.64 kilonewton. Using table 3.4, and K2 is equals 0.9 for a normal bolt. Then we get FTRD equals to 201.96 kilonewton. Finally, we check the interaction between shear and tension. Then we get 0.023. Since the total is much less than 1, we conclude the connection can safely support the load.
So as you can see, this is the drawing for trusses, beam, connection and column. And that's all from us. Thank you very much.